If you haven't viewed Jupiter through a small telescope, you should. There you'll see another world and small dots of light that are the moons of Jupiter. Those dots of light remain just that until we sent spacecraft to go investigate. I really liked the Galileo mission to the Jovian system. The 2 Voyager missions opened the door to Jupiter, but Galileo moved in and stayed a while, getting to know the place the same as you would learn a new city that you just moved to. So please take a few minutes and follow the long road traveled and the many discoveries of the Galileo mission to the Jupiter system. You know, it's amazing that the Jupiter Orbiter mission made it to the launch pad at all. The Jupiter Orbiter probe project received congressional approval on 1 October 1977. NASA's plan was to build and launch the Jupiter Orbiter probe mission by 1982. The JOP was to be transported up to Earth orbit by the Space Shuttle, then propelled onto a direct Earth-Jupiter trajectory by means of a solid-fueled inertial upper stage launch system. The JOP would reach Jupiter in 1984. In 1978, the JOP project is renamed Galileo. Named after the first scientist, Galileo Galilei, he discovered the 4 large Galilean moons, the first objects found to orbit another planet. Very quickly, the need for a heavier spacecraft is identified. For the 1982 launch, NASA developed a Mars gravity assist trajectory to conserve fuel. But the Galileo team had concerns over the shuttle's engines being rated to 109% to achieve the heavy lift needed to launch the now heavier Galileo. The use of the more powerful liquid-fueled Centaur upper stage instead of the IUS is considered, but NASA Administrator Dr. Robert A. Frosch opposed the use of the Centaur due to safety concerns. To solve Galileo's weight problems, NASA announced plans to separate the orbiter and probe mission and sets 1984 launch dates. But due to the cost of the extra probe launch and the cost overruns on Boeing's IUS, the orbiter and probe are recombined into one mission using a wide-body Centaur and postponing the launch until April of 1985. In early 1981, the new Reagan administration's Office of Management and Budget Director, David Stockman, proposes budget cuts, which, if approved by Congress, could force the elimination of the Galileo mission, other future deep space projects, and even JPL. But Senator Strom Thurmond and the Department of Defense both backed the Galileo project for its military benefits. Senator Thurmond informed OMB Director Stockman that the Air Force needed satellites with a survivable autonomous capability to remain operational during times of war if communications with the satellites was lost. In fact, JPL had already developed and applied autonomous technology for the Air Force in parallel with the Galileo spacecraft's development. At the end of 1981, OMB Director Stockman agreed to reinstate Galileo back into the fiscal year 1983 budget, but recommended that Centaur development be killed. This change was solely driven by budget pressures. NASA restructured Galileo for a mission without Centaur, making plans to use Boeing's solid-fueled IUS augmented with a solid-fueled kick stage for increased propulsion. The launch, scheduled for August 1985, would use an Earth gravity assist to reach Jupiter by 1990. Even as NASA made plans to use the lower-powered IUS, Centaur still had strong support for use as a space shuttle transfer stage. In July 1982, President Reagan signed a bill directing NASA to design, develop, and procure the Centaur upper stage and to stop work on the IUS for Galileo. NASA delayed Galileo's launch for another year until May 1986. Now that the Centaur question was finally answered, JPL set to work to meet the 1986 launch date. For the next several years, the challenges became more technical and management-oriented than political. At 3 a.m. on December 19, 1985, Galileo began the first 3,000-mile leg of its half-billion-mile journey to Jupiter. Galileo's management was concerned that the plutonium that powered the spacecraft would draw anti-nuclear protesters, or worse, a terrorist attack. The caravan crossed America without incident or mishap, reaching the Kennedy Space Center on the 23rd of December, 1985. Ahead lay the integration of Galileo with Centaur and other final tests. In late January 1986, Galileo was tanked up with hypergolic propellant, a very hazardous process, but Galileo passed the test. A few days later, on the morning of January 28, 1986, the Space Shuttle Challenger and her crew of 7 was lost. It was very clear to all of the Galileo team that the mission to Jupiter was on hold or may never be launched. No firm launch date could be set until after the Rogers Commission made its report to President Reagan in June of 1986.
This has been a difficult passage for America, but we will go on, just as the crew of the Space Shuttle Challenger would have wanted us to. We'll use every ounce of American skill, ingenuity, and gumption, and we'll work twice as hard and be twice as vigilant. We'll simply do what has to be done to make our space program safe and reliable and a renewed source of pride to our nation. America has a claim to stake on the future. We've suffered a tragedy and a setback, but we'll forge ahead, wiser this time and undaunted as the spirit of the Challenger and her 7 heroes.
NASA's view was that it would take until early 1988 for the shuttles to fly again, and Galileo would probably have to wait longer depending on where it ended up on the flight priority list. Also, in June of 1986, NASA canceled the Shuttle Centaur program. This forced Galileo to use the lower-powered IUS, solid fuel booster. JPL had anticipated that Centaur might be scrapped and had already initiated a series of alternative launch plans for Galileo. Without Centaur, a direct flight to Jupiter was impossible. Given the spacecraft's propellant capacity, only the Venus-Earth-Earth trajectory would work, and that flight path would take 6 years to arrive at Jupiter. Galileo was designed to operate at distances between 1 to 5 astronomical units from the Sun. The Venus-Earth-Earth gravity assist trajectory would bring Galileo as close as 0.7 AU from the Sun, encountering twice the solar radiation intensity as that found near Earth. Also, with a 6-year trip versus the 2-year trip via Centaur, the plutonium in Galileo's RTGs would decay more than planned, thus reducing their power output once Galileo arrived at Jupiter. The spacecraft sent to the Kennedy Space Center in April of 1989 was very different from what had been sent there 3+ years before. New software and substantial thermal protection changes were made. There were also large improvements made in equipment reliability due to the longer mission time via the Venus-Earth-Earth gravity assist trajectory.
Coming up next on C-SPAN, a news conference by the Christic Institute, the Foundation on Economic Trends, and the Florida Coalition for Peace and Justice. They announce a lawsuit attempting to halt a manned NASA space launch. The lawsuit is aimed at the launch of the Jupiter probe Galileo aboard the shuttle Atlantis, scheduled for October 12th.
The courts threw out the lawsuit. Galileo was finally launched on October 18, 1989, by the Space Shuttle Atlantis on the STS-34 mission.
And about this time I turned to look at Don and I said, "You didn't prepare me for this," as the tower went by a great deal faster than I thought it would based on my simulator experience. $4.5 million pounds or so of machinery and 6.5 or so million pounds of thrust. The roll maneuver. There was a great deal more vibration here than I expected, and I think it's probably acoustic. It shakes your body and your soul. The main engines throttle back, and as you reach maximum dynamic pressure, and there's some very good shots here of the waves created by the speed and the maximum dynamic pressure as we went through the area of max Q. SRB SEP, this is another area that Don failed to prepare me well for. In the simulator, there's a flash bulb or something that goes off when you get to SRB SEP, and in the real life, there's an explosion that goes off right in front of your face. It was wonderful, but it was surprising.
And get ready to launch the IUS. The first thing, a visual thing that we had to do was get the IUS up to 28 degrees, and that all went very smooth. The deploy time came, we flipped the switch, we deployed it, and it slowly went out of the payload bay. And at that time, both Ellen and I sighed a great sigh of relief because we figured Galileo was not our concern at that point. And then Don was getting ready to fly the shuttle and maneuver it away from the IUS and Galileo stack.
1 hour later, when Atlantis had flown to a safe distance, the IUS rocket fired, speeding Galileo into interplanetary space and onto its first objective, Venus. The Venus-Earth-Earth gravity assist trajectory presented new scientific opportunities for Galileo. During the 6-year flight to Jupiter, the spacecraft would pass close to Venus, Earth, and the Moon. Flying through the asteroid belt twice would allow Galileo to make close observations of at least 3 asteroids: Bosania, Gaspra, and Ida. Unlike previous planetary spacecraft, Galileo was designed with a dual spin feature. Part of Galileo rotated continuously at 3 RPM, which accommodated the field and particles experiments. The despun section of Galileo remained stationary, providing a fixed orientation for imaging equipment and other sensors. On the way to Venus, 2 trajectory correction maneuvers were performed. A third TCM was not needed because the aim point at Venus was virtually perfect. Data collected at Venus was stored on a tape recorder. The high-gain antenna remained stored and folded up like an umbrella. Keeping the high-gain antenna shaded and cool prevented the optimum orientations for data collection. The data would be transmitted with the 2 low-gain antennas when near Earth. 1 large and some smaller TCMs put Galileo on a precise path for an Earth flyby and gravity assist. This would be the first time that interplanetary spacecraft had returned to Earth, even if briefly. Galileo was able to provide new and unusual views of parts of the Moon. Images from Galileo proved that a huge impact basin did exist on the far side southern section. The 1,200-mile across basin was formed by a 100-mile wide meteor that struck the Moon's surface. It probably hit so hard that the Moon wobbled and lurched while it blew out a large chunk of the Moon into space. Astronomer Carl Sagan pondered, could life on Earth be easily detected from space? He devised experiments for Galileo to perform on this first ever flyby of Earth by a deep space probe. Galileo found the Sagan criteria for life: the absorption of red light due to photosynthesis, oxygen production as a result of plant activity, high levels of methane that would break down with oxygen present, and modulated narrow band radio transmissions that could not be from any known natural source. Galileo's experiments were to become future controls in the search for life on exosolar planets that would not be discovered until the middle 1990s. With Earth in the rear-view mirror, Galileo treks out into the asteroid belt and the Gaspra encounter. On the 11th of April 1991, commands were radioed to open Galileo's high-gain antenna. The motors turned on, but the expected signal confirming that the antenna had opened never came. JPL formed a high-gain antenna deployment anomaly team to review and study the problem, as the low-gain antennas were adequate, for the time being, to transmit data back to Earth. On October 29, 1991, Galileo became the first spacecraft to encounter an asteroid. Discovered in 1916, 951 Gaspra is one of the 5,000 objects in the main asteroid belt, a donut-shaped area midway between Mars and Jupiter. Galileo passed approximately 1,600 kilometers from Gaspra at a relative speed of 8 kilometers per second. Images revealed Gaspra to have a cratered surface and an irregular shape. At 20 kilometers long, 12 kilometers wide, and 11 kilometers thick, Gaspra is tiny compared to the largest asteroids. Gaspra's irregular shape suggests that it was broken off a larger body through catastrophic collisions. In December of 1991, Galileo would be the farthest it would get from the Sun for several years. NASA managers believed that the December cooling opportunity would provide the best chance to free the crucial high-gain antenna. After many hours of cooling, data sent from Galileo indicated that the attempt had not worked. NASA continued the thermal cycling attempts over the next several months with no success in freeing the high-gain antenna. Returning to Earth 2 years after its last Earth encounter, Galileo discovered a wealth of information about the Earth's geocorona, the outermost part of Earth's atmosphere. The diffuse hydrogen gas of the geocorona is forced in an anti-sun direction, creating a geotail extending 400,000 kilometers away from Earth. Galileo was able to image the northern polar region of the Moon in infrared and visible light, providing new data on lunar geological processes. Galileo also investigated a series of high stratospheric ice clouds over Antarctica. On December 8, 1992, Galileo once more flew by Earth, passing within 300 kilometers above the South Atlantic, finally putting Galileo on a direct trajectory to Jupiter and the encounter with asteroid 243 Ida. With Galileo closest to the Sun that it would ever be again, controllers ramped up their efforts to deploy the stuck high-gain antenna. Unfortunately, after all their efforts, NASA had to accept that the high-gain antenna would not release, and that the mission would have to continue on with the slower data transmission rate of the low-gain antennas. In spite of the LGA's slow transmission rate, project staff devised ways to complete 70% of the mission's scientific goals by squeezing more data into fewer computer bits with data compression. And dependable data storage aboard Galileo took on a new importance. Also, the Galileo team augmented data flow by improving the ground antenna systems of the Earth Deep Space Network. The Galileo high-gain antenna workarounds would end up becoming especially useful for the faster, better, and cheaper interplanetary missions of the future. On August 28, 1993, Galileo flew within 2,400 kilometers of asteroid 243 Ida. Ida is considerably larger than Gaspra, but is also highly irregular, measuring 56 by 24 by 21 kilometers. Like Gaspra, Ida is heavily cratered. Ida's cratering is more extensive than Gaspra's, suggesting that Ida formed earlier than Gaspra. Months after the Ida flyby, when Galileo's images were played back, Ida was discovered to have a small moon, which would be named Dactyl. Approximately 1.6 kilometers in diameter, Dactyl orbits about 100 kilometers from Ida's center. This was the first conclusive evidence that asteroids could have satellites. With Galileo's planetary gravity assist and asteroid flybys now completed, the spacecraft continues on to arrive at Jupiter on December 7, 1995. On March 24, 1993, world-class comet seekers Eugene and Carolyn Shoemaker and David Levy discovered a comet orbiting Jupiter. This comet was in the unusual form of a line of numerous pieces resembling a string of pearls. Further analysis showed that in July of 1994, the comet, now called Shoemaker-Levy 9, would smash into Jupiter. When this happened, Galileo, though still far away, would have an excellent view of the collision sites. The comet's fragments would hit Jupiter's night side away from the Sun. Because of this, Earth-based telescopes would not be able to observe the impact sites directly, but Galileo could. From the 16th through the 22nd of July, 1994, 21 pieces of comet Shoemaker-Levy 9 collided with Jupiter in an event that was spectacular and beyond expectations. The first comet fragment hit Jupiter at over 320,000 kilometers per hour, and it generated an intensely bright fireball at least 3,000 kilometers high. These impacts also resulted in hot bubbles of gas in Jupiter's atmosphere. They also left large, dark, scar-like spots that persisted for weeks. Some of those spots were 2 to 3 times the size of the Earth. The Shoemaker-Levy 9 event was the first collision of 2 solar system bodies ever observed, and fate gave Galileo a front row seat. On July 12, 1995, Galileo released its 750-pound Jupiter atmospheric probe. The spacecraft was 83 million kilometers and 5 months away from Jupiter at the time. In December 1995, the probe would become the first Earth emissary to plunge into the atmosphere of one of the solar system's gas giant planets. On July 27, 1995, 2 weeks after the probe release, Galileo fired its main engine for 5 minutes and 8 seconds, performing an important maneuver that would deflect it away from a collision course with Jupiter. This was the first burn of Galileo's engine, and it demonstrated the engine's operability. Firing the engine had to wait until the probe's release because the probe had been mounted in front of the engine. This maneuver was enough for Galileo to miss Jupiter by 230,000 kilometers. This would allow Galileo to fly overhead and receive data from the probe as it fell through the Jovian atmosphere. Galileo would then relay the stored data back to Earth. In August 1995, 63 million kilometers from Jupiter, Galileo observed one of the most intense interplanetary dust storms measured. Io's volcanoes appeared to be the source of the dust hitting Galileo's dust detector. In October 1995, Galileo's reel-to-reel tape recorder would not stop rewinding. A failure of the recorder, in addition to the failed to deploy high-gain antenna, would doom Galileo's mission. Project staff restored the recorder, but with less data storage space. This forced the cancellation of the close-up photos of Europa and Io to to be taken during Galileo's arrival at Jupiter. A tough call, but NASA could not risk losing the atmospheric probe's data. By the end of November 1995, Galileo had completely passed Jupiter's bow shock 9 million kilometers from Jupiter, and finally into Jupiter's space. Galileo now began its first direct measurements of the Jupiter system. December 7th, 1995, Arrival Day.